This is a magnet. It has magnetic field lines that move up from the top and go down through the bottom, like this. If I take a wire and cut it across those magnetic field lines, it actually creates a voltage in the wire. So if I hook up my voltmeter to the end of the wire, then sure enough, when I move the wire over the top, it creates a voltage. But only when I'm moving it. If I stop, then the voltage drops to 0. Or I can set the wire on the ground and move the magnet over the top and it creates the same voltage. But if I move both the wire and the magnet together, then they also don't create any voltage. So there has to be relative motion between the magnet and the wire. So in order to create this voltage, I have to constantly be moving the wire, cutting across the magnetic field lines. But what if I just replace this location of wire with a section that's always moving, like a disc spinning? So if this spins, I still need a way to connect it to the rest of the circuit. So to do that, I'm just going to put some wire brushes on the side. Then I'm going to stick this brush underneath that'll contact the axle spinning. So now my closed circuit goes like this. From the multimeter to this brush, across the disc, down this brush, back to the multimeter. Now for my magnet, I'm not going to use that giant magnet I had before. That's way too strong. But I'm going to use this uniform disc magnet. So I can apply a uniform magnetic field over the top of the disc here. Okay, now let's turn it on. So there's no voltage, but when I move the magnet over the top, then I generate a voltage. That's because my section of wire right here is continually cutting through the magnetic field. What I've created here is called Faraday's disc. It's an electric generator that was invented in 1821 by Michael Faraday, and it was the first device ever created that could generate electricity using the laws of induction. Faraday's exploration of this simple generator laid the groundwork for his later formulation of Faraday's law, which quantitatively described the relationship between changing magnetic flux and induced electromotive force, or voltage. But there was a problem. According to Faraday's new law, his own device created a paradox that still persists to this day. Let me show you what the problem is. But first, I'd like to thank the sponsor for this video, Drink Element. Element is a zero-sugar electrolyte drink mix born from the growing body of research revealing that optimal health outcomes occur at sodium levels 2 to 3 times government recommendations. Each stick pack delivers a meaningful dose of electrolytes free of sugar, artificial colors, or other dodgy ingredients. That is good. Taste it.
That is really good.
It's so good. Element is formulated for anyone on a mission to restore health through hydration. Element is even being used by professional athletes. It's the exclusive hydration partner for the USA weightlifting team and many other Olympic athletes. There are so many flavors to choose from, but one of the coolest, most unique flavors that they just introduced is their new Element chocolate medley. This includes chocolate mint, chocolate chai, and chocolate raspberry, designed to be enjoyed hot or swirled into your favorite recipes. It looks like hot chocolate and it tastes so good like a good chocolate drink, but it's actually an electrolyte mix. So if you want to try Element and their new chocolate medley, you can go to drinkelement.com/actionlab or click the link in my description to receive a free Element sample pack with any order. And thanks to Drink Element for sponsoring this video. Now let's get back to the experiment. Remember that when I moved the wire over the magnet, it created a voltage. And likewise, when I move the disc through the magnetic field of this magnet above it, it creates a voltage. But also remember that when I moved the magnet over the wire, I created a voltage. So the motion should be relative. I can either move the magnet or the wire, it doesn't matter. That should mean that if I spin the magnet above the disc while the disc is standing still, I should also get a voltage. So now I put this on the end of the drill and I can spin the magnet like this. So let's see what happens now if I spin the magnet over the disc. When I spin the magnet, I get no voltage generated. It's exactly 0. So that's not good, but it gets worse. Remember the scenario where I moved the magnet and the wire together? It didn't create a voltage. So now let's try that with our disc. What if I just place the magnet on the disc so they're moving at the exact same relative speed to each other? I still generate a voltage. If I just set the magnet on top of the spinning disc, they're both spinning at the exact same speed, so there's no relative motion between the disc and the magnet. But when I turn it on, I get a voltage. So when we expected to get no voltage, it's generating a voltage. And when we expect no voltage, there is a voltage. What's going on here? So the problem is this: if both the disk and the magnet aren't spinning, no relative motion between them, I get no voltage. But if I spin the disk and the magnet is standing still on top, then I get a voltage. But if I spin the magnet on top with the disk standing still, then I get no voltage. But then if I put the magnet on the disk so that they're both spinning and no relative motion between them, then I get a voltage. This is known as Faraday's paradox. It goes against our intuition and challenges the very heart of the physics that were first used to describe it. So let us see if we can resolve the paradox and understand why this is happening. Initially, Faraday proposed that when the magnet rotates, the magnetic field stays stationary. So the disk cutting through the field lines gives rise to an electromotive force, or EMF, observable as the induced voltage across the disk. But he later changed that point of view based on the fact that when you move a magnet linearly, the field also moves with it. So he thought that the field lines must rotate with the magnet as well. For example, if I spin this bar magnet under this magnetic viewing paper, we can see the magnetic field rotates with it. But if the field rotates with the magnet, then the spinning magnet should induce a voltage on a stationary disk. So which is it? Does the field rotate with the magnet or remain stationary? Well, it turns out that whether you view the magnetic field as rotating or remaining stationary, the paradox can be solved when we take the whole circuit into account. Remember that in order to measure the voltage, we have other wires that I'll call the closing wires, because these are the wires required to complete the circuit. Remember that underneath here we have a small portion of wire touching the axle. So there's a small piece of wire underneath here. So this piece of wire is cutting the magnetic field lines as well. So now with these wires taken into account, let's look at the scenario where only the disk is spinning. If the magnetic field is stationary or co-rotating, we would get the same result since the magnet's not spinning. So the disk cuts the magnetic field lines and a voltage is induced. And the closing wire is neutral because it doesn't cut any magnetic field lines because it's not spinning, meaning it's not moving through any magnetic field lines. But now let's look at the scenario where the magnet is spinning and the disk is still. In this case, if the field is stationary, the disk is neutral since it isn't moving through any magnetic field lines, so there's no induced voltage. But if the field is co-rotating with the magnet, then the disk is cutting through the magnetic field lines and there's a current induced. But also, the closing wire is cutting the magnetic field lines as well, and it's polarized the same way, so no voltage is induced in the circuit. And finally, if both the magnet and disk are rotating together, and we take the scenario that the field is stationary, then it's the same as in the scenario 1 where just the disk is rotating, and the disk cuts the magnetic field lines. And if the field is co-rotating, then the disk doesn't cut the magnetic field lines, but the closing wire does. So there's still a voltage induced, which is what we see experimentally. So we can see that in either case we can resolve the paradox whether or not we view the magnetic field as stationary or rotating when we take the whole circuit into account. So there really is no paradox. So why did I say that this is still being discussed today? Well, because physicists can't agree if the field is rotating or not. You can see that experimentally we expect the same results. So we can't tell from this experiment whether or not the field actually rotates with the magnet or not. And it turns out that almost any experiment that you create, you wouldn't be able to tell that the field is rotating or not rotating. There are well-reviewed published papers that say it does rotate with the magnet, and others that say it doesn't. And then others say that the magnetic field lines don't exist at all, but they're just used as mathematical tools and not a real entity. So it's pointless to discuss whether a field rotates with the magnet or not. Until then, we can just have some fun making the motor version of Faraday's disk by sticking a magnet to a battery and touching it with a wire. And thanks for watching another episode of the Action Lab, and we'll see you next time.